Okay, today I do one more time on this model power method after we get pointed out some question again. So I will look on my previous example. So I think it's better for me to redo the video to clarify some of the question. Okay. Now this model power approach is actually trying to, what you need to do, the procedure is actually we will check every test profile, which is like our borehole. Okay, then we will apply this correlation factor to the calculated resistance to obtain the characteristic resistance, right? But for the model, for the alternative method, we actually use the model factor. We don't use the correlation factor. Okay, we have covered the alternative procedure. So if you don't understand what this clause is talking about in the code, we will go through the example. It will be easier for you to understand. Now, so the first method is we need to calculate the resistance. Okay, this is a calculated resistance. Okay, by using whatever method, the prediction method, the alpha, CU, beta, sigma, prime, whichever method that depending on the soil condition. Now, take note of this symbol is RC calculated equal RB calculated plus RS calculated. Okay, these are all calculated base resistance and shaft resistance based on the ground test. Okay, it is not the characteristic, it's not the design resistance. Okay, read this underline statement, very important. They include the model calibration factor. Okay, take note, model factor, calibration factor, correlation factor, they are different. So model is actually calibrated calibration factor. So in this method, right, we don't apply anymore the model factor, or actually the model factor is equal to 1. Okay, so all the result is the predicted resistance of a pile. It will exactly at the location of the profile of the ground test. Means we actually assume the soil profile that you adopt is the representative of the ground condition. Okay, so this pile is called a model pile. Okay, it's a model that represent the whole other conditions. Okay, so model factor is equal to 1 in this method. Okay, then how do we calculate the characteristic values? Okay, the characteristic values depends on the correlation factors. This correlation then again depend on the number profile of tests, which simple fact is actually the number of boreholes that we have. Okay, so we will take the mean. Okay, divide by this correlation factor number 3, and also the smallest calculated value divided by the correlation factor number 4. Okay, so from there on, we know what is the characteristic resistance of this water pile. Okay, then from there on, we will actually deduce the respective base and shaft resistance, the characteristic shaft and base resistance. Okay, now we still need to apply the partial factor, which is the R4 factors, to the characteristic shaft resistance and base resistance. Okay, so this is no change. So we apply to the characteristic to obtain the design. Okay, so this one is always calculated characteristic, then obtain the design. So this sequence of thoughts you all must have. Now to make go back to the previous example. Now I add in 2 more boreholes. Actually, there are more than 3 boreholes, but I just for simplicity I add in 2 more boreholes. Okay, assuming also talking about the 800 mm per meter power. Now, so I give you the bore log in individual borehole. You can notice that this is borehole 1. We have soil. Then we have a boulder in the middle, and then we encounter rock. Okay. Borehole number 2 is residue soil all the way, and we did not encounter any rock. Now, borehole 4, you know, we have a boulder, a very big boulder, 7-meter thick boulder, before we hit the soil, and then we hit the final rock next. Okay? And the rock head is very high is about 20 meters below ground for this borehole number 4. Now, I need to make some assumption. So now we have to, let's use the alpha CU method. Now, in this table, I summarize for you for these 3 boreholes, borehole 1, 2, and 4, the depth, the soil type, and also then the correlation to the CU. Now, I have equate we assume this length is about 33 meters first, because 33 meters, you notice from this borehole, 33 meters, we will just go into the rock about 1.5 meters for borehole 1. We are actually about 4 meters into SPT 100 for borehole 2, and we are actually very deep inside the rock for borehole number 4. So you can see, because these 3 borehole is totally different from each other. Okay, one have a very low rock head, one has totally no rock, and one with a very high rock head. By looking at the bore log, you already know the site is not homogeneous. But you are trying to do, by using the model pile method, you are trying to find a pile that is actually, and you can actually try to design a pile that actually represent all the soil, they can cover all the soil condition. Okay, so let me bring you through the procedure first. Now, first of all, we need to calculate the mean of the CU along the shaft, which is about the 33 meters. Now, the rock, there's a QC values, okay, there's a unconfined compression stress result. Half of the unconfined stress result is the undrained shear strength. Now, you notice the undrained strength is very, very high based on this thing, based on this QC over 2, which is natural, okay? So you see the mean CU along the borehole number 1 is about 3,761. Very, very high, right? But you see borehole 2, the mean CU is about 206 kPa only. For borehole number 4 is even higher, is 7,000 over, because it's predominant into rock. Okay, so now you take the overall mean, okay, which is you take the mean of these 3 boreholes, the CU, you get the mean CU is a 3765. Okay, so the alpha for 3765 or 3761 is about 0.35. So all we use alpha 0.35 because the CU generally higher. Now, if you use the alpha CU, you notice that if you go to use this to the mean CU is very, very high. The friction is 1,003, already exceed the limits that we actually impose in our design, which is 250 and 400 for the rock. Now, which number you need to use, whether 250 or 400. Remember, we are trying to model a pile or design a pile that represents a whole site. So on the conservative side, you should use 250. Okay, that means to say you assume the everywhere is the soil, okay, and limit by the soil friction first. Because you won't, in actual fact, in actual site, you won't know whether you are encountering rock or soil before you actually bore. Okay, so now you take a look at the mean CU at the base, at the pile base, it's very high, it's 33,000 over, okay. The minimum is a borehole 2, which is 500. And again, the base resistance for this mean is extremely high. If you use 9 CU, it will exceed the rock limit resistance also for the soil. So we will use the soil first. Now, remember, a model factor in this case is 1. So assume a length of 33 meters, you calculate the resistance for every single borehole, So I generalize this to a generic equation, which is about 89.94 multiplied by the mean shaft resistance and 0.502 of the base resistance. Now, so you see, for borehole number 1, the mean shaft resistance is limited by the 250. The base is also limited by the soil, which is 6,000. So you'll notice that actually borehole number 1 and borehole number 4, even though borehole number 4 has a very, very deep rock socketing we calculate the resistance is the same as borehole number 1 because they are all controlled by the limiting friction and end bearing resistance. Now for borehole number 2, you notice is significantly lower. It's about 1/3 of the borehole 1 and 4. Okay, because they are all based on soil only. Now in this case, after that you take the mean of the 3. Okay, because of the 3 borehole, you take the mean, you get 18,575 km, which is very, very high. Okay, because predominantly is rock. Predominantly is governed by the rock. Even though it's governed by the rock, but it's governed by the is limited by the friction for the soil and end bearing for the soil. Now you look at the minimum. So the minimum is borehole number 2 is 8231. Now so now you apply the correlation factor. Okay, you notice that from this case you look very simple is that the minimum value will govern. So if the minimum value govern means actually it already tell you the site, the variety is more than 10%. The variance is more than 10%, which is quite obvious, right? I mean, you will see, you don't need to calculate. You just look at the borehole itself. You know it's going to have a huge difference. Now, then you calculate the characteristic shaft resistance based from this overall characteristic resistance. Okay, so actually is you get a friction shaft resistance is 4490 and the base characteristic resistance is 1699. Take note the code. The code will tell you say that a careful examination of ground investigation does not enable different homogeneous area to be distinguished. These characteristic values are those adopted for the whole entire site. In this case, we got 3 boreholes with totally 3 different conditions. But what this standard is trying to say is that if you have really large number of boreholes and you can actually identify different homogeneous location, you are actually able to do a different zoning. Okay, and so you have different model power. So for our case, we can identify different homogeneous site. One area with rock and with soil. So we simply divide the site into 2 parts, with rock and with soil. We disregarded whether this rock is very high or very low. Now, so we calculate. So the first estimate, assuming the whole site is homogeneous, you calculate the action. You calculate the resistance. You notice that in all 3 conditions, C1, C2, and the shaft check only, they all pass. And you can see from above, the C2 governs. Okay, the case Combi 2 governs with an over design factor of 1.78. That means to say we have buffer, we can actually reduce the length. But you will notice if you reduce the length, all your mean friction will reduce. For borehole number 1, you will not anchor into rock anymore. You probably only in the soil. And you cannot remember from the soil, there's no SPT 100. Its maximum is SPT 67. Okay, you can reduce. Okay, you have to reduce and check again. But let's take it that we accept this safety factor. We are comfortable. We are being conservative. There's nothing wrong with that. Now, take a look at this clause. This clause, first you read, maybe I also feel it quite confusing. If I read out for you, if several profiles of the ground tests are available, means you have several boreholes. The first estimate of an overall characteristic value based on all the profile of the ground test might lead to different homogeneous parts of the site being identified. Like our case, you already by calculation, either by calculation or just by visual checking the bore, you will know there's a different homogeneous. So some area you find a lot of rock, some area you don't find rock. But in our case, we only had 3 boreholes, so we can't really zone in this manner. So in this situation, the procedure started again for step 2 for each homogeneous part of the site. This can result in less conservative characteristic values than would be obtained as in the first estimate, which we done so just now. We done so. The first estimate, the whole soil condition were assumed to be the same. We assume, right, whether it's soil or rock, we assume they are all soil. It's the same over the site. So we have this characteristic value and is governed by the minimum value. You can see already, right? So what it means are actually in subsoil condition, especially the competent short-term, they are not homogeneous. So at different geological formation, you may have Fort Canning Bordeaux clay overlying the Jurong formation or Bukit Timah residue soil overlying the granite, like in our case. The first estimated characteristic resistance will actually naturally reveal the different soil type. Very obvious one. So this estimate usually shows the minimum value govern, which is true. So you see, you have soil, you have rock, confirm, no need to check. You also know the soil will govern, given the shelf friction and the end bearing are lower. Now, if there is enough boreholes, can you imagine, let's say today you have 10 boreholes, they all show rock and soil. Then you're able to calculate the characteristic value for one for rock and one for soil. But because you have 10 boreholes now, your correlation factor are smaller, resulting you have a bigger characteristic resistance. So actually, you end up with a less conservative characteristic resistance. Okay, so let's say you have 10 boreholes, 5 boreholes show soil, 5 boreholes show rock. Okay, so just nice, you can see half the size is rock, half the size is soil. So you calculate for the soil, 1 model power for the soil, 1 model power for the rock. But you don't divide by the correlation factor based on 5 boreholes for the soil. You divide by 10 because you in actual fact you did 10 boreholes. Okay, so you can notice that the correlation factor is much smaller if we use a 10 borehole. Also, this is what this clause is trying to say. So let's go through another round of the exercise based on this approach. Now, we try to separate the soil and the rock now. Okay, we still assume the length of 33 meters. Now, we calculate the mean CU along the shaft for the soil alone. So you can see for the first borehole, the mean become 102 only now. For borehole number 2, remain 206. For borehole 4, it becomes 73. But because they all have different CU, the alpha value are slightly different. You end up with different shaft resistance. Okay, shaft friction. Now, the mean CU for the rock along the borehole, you only got 2 boreholes with the rock. So your mean is still very high. Your shaft friction for the rock is still very high. It will exceed the limiting. But since this is confirmed is rock already, instead of 250 for the soil, we use the limiting value for rock, which is 400. Likewise, for the base, you can use for the divide for the soil and the rock. So for rock is very clear, it's still limiting 8,000. For the soil is 4,005 in this case. Now you notice just now the difference. Just now we use 250 and 6,000. Because we treat the whole site is controlled by soil. But now after we divide soil and rock, we actually segregate the two already. So now this generic equation is different already. So it becomes the mean friction multiplied by the soil length and the rock socketing length multiplied by the friction in the rock. Then of course, depending on the base, whether it's soil and rock, we use according the base resistance. Now take a look. So we go through this equation, so it's become a more lengthy equation. For borehole 1, because majority is soil, you see the first part, 31.45 meter is soil. The shaft resistance is only 51. The rock is only 1.55. Then the end bearing is in rock. We get only 9,605 compared to the first estimate, which is 23 over 1,000. You may first think that, how come now this is actually more conservative than the first one? Because we have, in actual fact, we already segregate the 2 parts, the soil and the rock. Okay, the first one, even though it's very conservative, even you get a very high RC for the calculated resistance for borehole 1, they are not governing. Okay, later you'll go through. For borehole 2 is the same. Okay, because it's all soil. For borehole 4, also there's a rock. You notice now it's also reduced. It's become 20,000 instead of 23,000. Because we have accounted for the soil. Now, so what is the mean resistance with the rock? That means if you encounter rock, it's borehole 1 and 4. The mean becomes 15,000, 19 and 4. The minimum is borehole 1, which is 9,600. So now you have 2 resistance. two characteristic resistance. First is the one with rock, which is you calculate the mean for the rock and the mean with, or the minimum with the rock, which is 7,222. Okay, so now this is for the rock. So you will use this resistance whenever there is a rock. For the characteristic resistance with soil only, this is reduced further because you notice the mean and the minimum is the same because we only have one borehole showing soil. So actually the mean and the minimum is the same, but because of the correlation factor is higher for the mean, you end up with a lower characteristic resistance for the soil, which is 5796 compared to the 6,000 over kilonewton previously. Now in this case, we created a model pile in soil and rock. Okay, so in your drawing, you have two design resistance, okay, for soil and rock. So assuming you can identify with high confidence, okay, this location is soil, you will calculate. Or you every house you will design two. One is assuming there's a rock, one is assuming there's no rock. Okay, to using this Waterpower approach. So we have created two Waterpower, which is more accurate, okay, but it will be more work. Okay, it will be more work. So summary. The whole idea of the Waterpower is to create a Waterpower that represents the whole site condition. This method assumes a homogeneous site condition by comparing the mean and the lowest value. Now, you compare with the alternative method. The alternative method don't talk about mean, don't talk about the minimum value. We calculate the borehole and apply the model factor. Okay, but in this case, Waterpower method, by taking the mean and the lowest value, is like a statistical approach. We calculate what is the average value, then we see the minimum and see which one is governing, which is quite a common sense method. It's in actual fact is it's almost like using the most conservative borehole for design, like what we do previously. We take the, if you want to be a super conservative design, or you are short of time, you have 10 boreholes, you will use the most conservative borehole to design for the whole site. It's essentially the same. Okay, but if your site is quite homogeneous, meaning you cannot really identify which one is the most conservative borehole, you take the mean and you check accordingly. Then you'll find out sometimes your mean will govern. If your mean govern means your site is quite homogeneous, the variance is less than 10%. Okay, technically speaking, you use this method, right? You don't need to zone the site. You don't say, oh, this zone belongs to this borehole. I use this borehole to represent this zone, that zone. You can don't need to do this because your model power technically has captured all the possible soil conditions. Okay. So this is more suitable for a relatively homogeneous soil condition, like a single geological formation like OA. Okay, which is quite rare in Singapore that you only have OA. Sometimes you have garland formation overlying the OA. Okay, so this is what I concluded by studying the code and trying to work through a work example. In actual fact, I never use a Waterpower approach, and I have checked with many of my counterparts, including some professors. They also never adopt the Waterpower approach in real practical project. It's only in theory we learn about this thing. Okay, you notice that although it's a very good concept, it's a very logical concept, but when we try to apply to site, when your site condition changes, how are you going to react? Your average, your average CU, all these things will change. So you will have to go through a lot of iterative process, which can be time consuming, right? Because if along the way, sometimes in the actual project, you have additional borehole. When the new additional come in, whatever previous calculation you have done, you have to redo because your correlation factor will change. Your mean will change, right? So compared to the alternative method, maybe the additional borehole, you just check the power length based on the additional borehole. It will not affect your other existing design. This is what I can think of. Okay, so we are all learning. I thanks Wiki very much for asking this question. also made me learn something about model power. Also pointed out from my first video that, hey, how come the model factor is still, we still apply a model factor, which I study in detail. Actually, we do not need to apply the model factor for model power approach. Even called model power approach, we don't apply the model factor, which is quite interesting. Okay, so everyone is learning. I hope you can learn together. If you think my approach is wrong, you think you have a better approach, you can come and share with us. And I hope to hear from you. Then we all can learn together. Okay, but to be frank, out of my so many years of doing foundation, there's only one company use this method. Okay, I only come across one company use this method, which I have no chance to check whether he actually adopted correctly. He may have actually his inbuilt assumption, which I cannot check. Okay, so that's all for this additional Q&A that include the model power method. Okay, so thanks. You have any question, you just email me, or you can leave a comment in the video, in the YouTube, or in my Facebook, in my LinkedIn. Okay, thank you. Have a good evening. Bye-bye.